Okay, I would like to welcome you here on my presentation about asynchronous development in .NET Framework. I hope that it will be just some refresh for you, but there will be some topics that are maybe less known, and I would like to go a little bit deeper in some topics to show you how the async await tasks and the TPA programming works in general and in .NET specific. So I will start with one picture. Anyone knows what's that? I know it's written a lot of left, but anyone knows this specific?
One of the first microprocessors.
Perfect. Yes, it was one of the first commercial successful microprocessors, and it's 4 bits. It got about 2,000 processors, 45 instructions, and it was quite simple to develop for this kind of hardware because you just prepare a program, probably in assembler, directly, and then you just execute it, and the processor will process one instruction at a time and continue with another one and do probably what it's made for to create some kind of calculator or some simple device. But today the development is quite harder because, for example, if we take a look for some modern processor like in the current iPhone, they don't have thousands of transistors. They've got about 3 billions of transistors, which is quite more complex. And of course, instruction sets are much complex. And in general, there are quite more components that we need to work with. It can be file system. It can be some network components. Basically, just an USB hub is extremely complex stuff because you can connect lots of devices, and basically how we develop application is changing. Also, most of your devices don't have one core, but got multiple cores in the processor, and there are huge amount of stuff. At least we don't need to care about a lot of it because it's somehow automated. But there are some concerns we need to design if we want to write some application that works well with today's computers. There is also one extreme that is related to the servers, because we are writing server applications mostly, and these server applications can run on the servers with a huge amount of processors, and it should be able to handle huge amount of requests at the same time. It's not unusual, for example, to have Intel processors, Xeons, with 100 processors, 100 cores, not processors but cores, and that's pretty standard stuff on some high load servers. So in the beginning, I would like to ask you, who is developer here? Who writes applications? I hope that people who didn't raise their hands will not be bored too much, or they will be, but so you can leave if you want. And who writes some kind of multi-threading applications? Okay, basically everyone should raise your hand, because if you've written any web application, there you've already written some multi-threading application, because most of the web servers can process multiple requests at a time, and it's in most cases done by different threads assigned to the different requests. Okay, so I will start with something quite obvious, but we will get to some details. It's not like writing simple assembler code anymore. You need to use operating system, because we need to run multiple applications at the same time, share some resources, and also if we are running multiple applications, we need some isolation, and that's basically what the operating system helps us with. So in the operating system, each process has some isolation levels, and they've got it's got their own threads assigned, some parts of the memory, file system handles, TCP/IP sockets, and other stuff that we can work with, and that is assigned to the process. When the process ends, all these resources should be released by operating system. Okay, so this is some basic states of regular thread we can use from .NET. In .NET, of course, threads are quite simplified, so you don't need to care about some really low-level stuff. But still, you can use threads and basically extract the power from the processor you would like to use. Basically, thread. You can have unstarted thread, which is not thread yet from the operation system perspective. But if you started it, there is some allocation of resources for the thread, and then you can the thread is running. You can do some blocking waiting like join, sleep, etc. You can suspend thread and you can stop thread. In most cases, you would like thread to be stopped in some good way, not like aborting thread, which can cause some problems, but it also happens. So the main feature is that if you start thread is running, you don't need to care about planning thread, because it's not like one core is one thread. Currently, operation system do a lot of context switching, and on each core there can be lot of threads running. If you look at your operation system, there will be probably hundreds or thousands running thread at the time. But most of it will be in some sleep mode. So the thread will be there, but it will not consume your CPU power. When you should use threads in your .NET application? Definitely if you want to have some low-level control of what is done. In most cases, it's when you really want to extract all power from your multi-core processors. So, for example, if you want to write some application that do some hardcore algorithms that really needs to consume all the power. In other cases, you don't want this. So, for example, if you've got some web application, you really don't want to just get all power from processor, because it will be really slow to process multiple requests at a time. Also, quite a good thing, and something that a lot of developers don't do is that if you are creating new thread or disposing old thread, it's quite intensive operation for resources. So if you really don't need this low-level control, don't try to create new threads and then stop it, because it's quite expensive for operation system and for your computer to do this. Another thing is if something in your thread fails, it will stop your application. And that's one of the common mistakes in web applications. I saw million times, and it's like someone needs to do something on the background, so they start their own thread, which is perfect. If it's not done too often, it will probably not affect the performance. But if there is some kind of exception in this thread, it will just crash the whole application pool, and that's not really a good thing for your application. So that's something you need to take care. If you are willing to create your own thread, make sure you will handle correctly all exceptions. Also, in the modern computers, you can probably have a few hundreds, maybe a few thousand of threads, but still it's quite a waste of the resources. So if you got, for example, more than 100 threads, it's really something smelly about your design, probably. If you are not creating some system for 100 cores, then it's really something you should not do. In most cases, using any ARM threads, it's not a good practice. Okay, so I will start with some simple demos, and we will start with the lowest abstraction we can get. That's working directly with threads. Okay. So maybe I will start just with showing you what can happen if you just create new thread. Throw an exception. And what happens if I start application like this? Okay, your application will just crash. So just make sure you take care about what happens. It's not like if for example your HTTP request code processing fails, it will just handles the current request as 500 internal server error, but it will not break the whole application pool. If you create your own thread and that fails, it will break your application, and the application gets restarted. And there is something called in IIS rapid fail protection. Anyone knows what's rapid fail protection in IIS? It's that magic feature that breaks a lot of applications because it means that if your application pool, I don't remember exact numbers, but it's like if it fails for 3 times in 3 minutes, it will just stop your application pool and don't start it again. So that's the default settings. Okay, so back to the threads. I've got few demos prepared here. So in this first demo, I will just create 24 threads. I've got four cores in this laptop, and I will just create 24 threads and then try to calculate P, which is not quite a good idea, but it's quite a CPU intensive operation, so it's quite a good for demo. After all threads will end, that's done with the join operation when I will just wait for all created threads. Then I will try another approach, which is quite different. It's having just 4 threads, which is exact number of my cores, and on each thread I am doing this operation synchronously 6 times. So it's also 24 things, and then I will just join it. And the last example will try to do less than my current count of cores. So 3 cores with 8 operations per core. Do you have any predictions which solution will be the fastest?
I think middle one.
Core minus 1.
First one.
Core plus 1.
Okay, I will just run the code and we'll see. I also got here Process Explorer, so we should be able to see what is happening. Okay, so it took 12 seconds, and we can see that all cores have been used. It's a little bit waste because we really use 24 threads, and it's just too much. Basically, everything in the operation system was sharing with the 24 full utilized threads. We can try another one. So you can see it's also, and it works in 13 seconds. Sorry. So it's a little bit slower. If we run it 1,000 times, it still gets a little bit slower, but only because there are some other components in the operation system. And if you create 4 threads, maybe some of the components of the operation system will just store some CPU time on one of these threads. But if you just push there 24 threads, you will just take everything or most of the resources. So probably if we set to the thread some higher priority, it will be the same, or there will be only just small difference. So it in general does not make sense to allocate more threads if you are doing really full CPU utilization than you've got cores. Okay, and the last part is doing 3 threads. And you can see we are not fully using the CPU. It's not exactly 75% because there is something that operation system does all the time. So there is some missing. There is some missing utilization, but still we can see that if we didn't use all cores, then the CPU is not fully utilized. Okay. And it took 15 seconds, so it's a little bit slower. Okay.
I didn't catch the meaning of these examples. It was about not using more threads than there are CPUs.
It was about showing that if you really allocate the thread can really full use core. It's not like, for example, consuming 20% of it. It will really use it. So it's good if you really want to do a low-level approach, at least the lowest you can do from regular .NET.
Or basically, if you are compiling something with GCC, you use the switch plus 1 core to really use all CPU and be fast.
Then you can break the operation system.
Is it possible to discover number of cores?
Yes, of course. It's, you can read it from the configuration.
Doesn't .NET have a function to automatically start a new core if it's needed? Automatically choose a number of cores, number of threads.
It's there. But for example, if you look at some, it's really not in the scope of the session. But in most cases, you can, for example, configure it based on some kind of virtualization, and for example, if you've got some really CPU intensive software, it's mostly configured manually. It's exactly like, for example, if you are configuring Nginx servers, there you can. The recommended approach is to set up as many processes as you've got cores, and it really depends on the situation. Okay, one more thing is related to using directly the threads, and that's the background threads. You can set the thread as the background one. You need to do it when you are creating it. And anybody knows what happens if you've got background thread? What's the difference?
Yes, I do. If this thread is a child thread, the parent thread should not wait before the thread continue and can terminate its code.
Yes, exactly. Basically in .NET it's done like your application will exit if all foreground threads will end, and it will kill violently the background threads that are running. It's the protection, so it does not happen that you, for example, close the main window of the application and there will be still some background threads running and the application will never stop, for example. But it's not like that the background and foreground thread have, for example, different priority. You can set priority to both background and foreground threads. It's only about how the application will end. Okay, so related to background threads, I've got just simple demo here. So I'm just creating 5 different threads and then just ending the main console thread. So if I do it without setting it as a background thread, we are waiting for the new created thread, and after it ended, the application will end. If I set it as the background thread, it will end immediately, because after ending this method, it will exit the main thread, and the all background threads will be terminated. The reason why I'm talking about it is because if you are using, for example, tasks or work items from thread pool in .NET, then everything, all of these contracts will be defined as running in the background threads. So the main idea is that in the main threads you need to take care about synchronization and waiting for background threads to finish and, for example, to somehow shut down your application. Okay, the last part related to using threads directly is the thread pool architecture or thread pool design pattern. It's basically way how you can have some set of threads created, and when you need some thread, you just take it from the pool, and when you don't need it anymore, you will place it back. The good thing about this is that you don't need to create new thread, which is quite resource expensive each time you need it, and you can just use threads from the pools. And of course, you don't have the full level control of the thread, but in most cases that's quite okay. It was this command thread_pool.q user work item, but if you are using C#, I don't know how many of you remembers this q user work item command. Is there anyone? Few people. But in the modern versions of C# and .NET, you will probably use tasks directly, which is the next part of the presentation, and basically which is the recommended approach when you are writing asynchronous code. Okay, one more thing related to thread pools. There is not just one thread pool in the .NET. There are many thread pools in the .NET and operation system, IIS, and a lot of components of the system. And you are using it basically if you are creating even the simplest ASP.NET application, because there are thread pool for threads that will, for example, process the HTTP request. So, for example, ASP.NET MVC, you've got controller, you've got action, and when the request hits your server, it will take the thread from this thread pool, and it will be used to process given request. Okay. So, related to thread pools. I've got two parts of the code. In the first part, I will just create the new thread, set some event, and wait for this event, and then do it for another thread, and do it for 50,000 of threads. Then I will do exactly the same, but not creating the new threads. I will use this thread pool to allocate some thread for it. Let's see what's the speed difference. Okay, so 50,000 threads. It takes some time for 50,000 operation. It's 7 seconds just about allocation, and you can see that for using the thread pool, it's 300 milliseconds. So there is quite a big difference. So I would recommend you to not use the thread if you really don't need to. Not telling that threads are wrong. For example, if you are writing some low-level library that needs to communicate with some network components or needs to do some controlling, then of course the thread will be probably the best you can use in .NET. But for the regular jobs or regular code, you should probably consider using tasks, or in the older versions, queue user or item from thread pool. Okay, let's get us to the tasks. Tasks are currently the preferred thread in asynchronous operation abstraction. So why thread and asynchronous operation? Because tasks don't need to be only some code running in some thread. It can be also waiting for some asynchronous operation that does not need currently the thread. So, for example, task can be waiting for some data came over the network, or task can be some part of your code that is running in some thread. It really depends on the situation, and tasks is, for example, if you are working with JavaScript, task is it's like the promise in the JavaScript. It's just the definition of some operation we can wait for. It's some operation that can be someone completed. But in most cases, if we are using directly tasks like task.start and things like that, then under the task there is some running code in some thread selected from some thread pool. There is one quite improvement because the tasks can return some values. That's something that you cannot do with threads or this queue user work item, but of course you can somehow put it to some variable, then synchronize it, signal something to another thread that the value is ready, but it's not so convenient to use like task. That task can always end up with some result, and the result is even that it's faulted or there is some result. You can have void tasks, which is just task without the generic parameter, but it also got the state if it's faulted or completed successfully. Quite a important thing is that tasks can be chained one after another, and that's basically how the async await works in .NET. So you can tell that after this async operation, task operation ends. So for example, after some of your code finished, or after some data from the network will be received, then continue with some another task. That can be also some delegated code or some asynchronous operation. Tasks are scheduled, which is another improvement, because if you create, for example, 50,000 of threads, your computer will break or application will break with some out-of-memory exception. If you create 500,000 tasks, it will not break, but it will not run them all at once. It will be scheduled, and the first task you have added to the queue will be processed first, and then after that there will be some others processed. And these scheduled tasks, there are some internal schedulers that will try to optimize the number of threads based on your performance of the computer and based of how what resources are consumed by different tasks. So, for example, if you've got some code that all the time just consumes all CPU it can, then the task scheduler will probably not allow to run more than a number of cores in your computer of these tasks. But if you've got some task that just waits for something, then it will probably run a lot more tasks at the same time. This can be configured, so you can define these rules, but in most cases you should be okay with the default scheduler. And one more thing is that task supports cancellation. And that's pretty important because that's some way how you can cancel asynchronous operations and some code, and it's basically passing some cancellation token to the task, and the task itself can somehow work with the token and can react when you send some cancellation request to the thread. Of course, it's not like it can safely end all of the tasks immediately. But for example, if you've got some processing task, you can place there check for a cancellation, and you can cancel the work in a good way and not just breaking the thread, like the thread abort exception and things like that, which is quite unpleasant because it can break the state of your application. And the most important from today's topic perspective is that tasks are basically designed, or the async await is designed to work with the tasks. So if you are using async await, it's using tasks, or to be more, it's not just tasks. It can be other types of objects, but that's not important right now. But in most cases, you will use async await with the tasks. And there is also some parallel link queue and some other stuff that can help you parallelize stuff that's defined in some task. I will just show it in the demo. Okay, so in this part, I've got just two samples because there is this 4 cores processing with the threads, and then there is the processing the same functions but using the threads. I'm using the task.run. We will use some default scheduler, and it will create the task, and then I will just use the task wait all, which will block this current main thread until all of these tasks are finished. Okay, let's see how fast it is. Okay, so first there is this using threads directly. You can see it also consumes all CPU. Okay, and then we will use tasks. It was the 13 seconds. You can see the utilization is also on 100%. Okay, and it's basically the same. So the task scheduler will try to optimize the number of parallel running tasks as best as it can. And the big difference is that for a task, if I change, for example, number from 24 to 1 billion something, it will probably work. It will just take a long time, but it will not break your application. If you are working with thread, you need to be more careful because you are really working with some operation system resources. Tasks, you can have a huge amount of tasks, and scheduler will take care about running it in some convenient way. Okay, just one more thing related to tasks. I also talked about Blink, which is parallel link queue, and you can simplify the code I write here. With something like this, and that's basically it. Because you can use enumerable, which will just define enumerable with 24 items, and then with the S parallel you will create the set of the tasks from the enumerable. That's input from the range. And then you can just define what should happen for each of the items, and this will create the task for the items, and it will just do it in exactly the same way like we did it here. So it's quite nice for some parallel processing, but this parallel queue is not great for everything, but it can help you if you are dealing with some problems related to parallel programming. Okay, there's one more thing. If I will just create one simple task here. Then there is some properties like is completed, is faulted, is cancelled. In most cases you don't need to deal about it because there is, for example, wait method. We used something similar here, but if I will try, for example, to wait just one task, then this wait is really important because if there will be some kind of exception here in the task, then your application will not know about it until you read the exception. And exception can be read, for example, this is wait, because this wait will throw the exception that was thrown inside the task in case there was some problem that the task failed. And it's quite important to not just create tasks and forget about it. It's really important that you just read the results of the tasks and wait for the task to be finished. Because if you just do something like this and there will be some kind of exception inside of the task, it will just fail and you will never know about it. And for example, if there is some other part of application that waits for the task to be finished, then the other part of the application will wait forever because this task will never run to success state.
So if you run the tasks and then an exception happens in one of the tasks and you don't catch it with this wait, it will continue running the other tasks behind.
Yeah.
It's not waiting for anything, it just discards the exception.
If you've got different tasks, it will just, one task will be failed but other will normally complete, for example.
Okay.
Also in older versions of .NET, if you did something like this, it break your application or your application failed because it was like some kind of, you didn't absorb the exception from the task, your application needs to be terminated. But they probably don't know exactly why, but then they remove this and it will just ends in some void, and you will never know about it. So it's quite a good thing to take care about task and not just use it as fire and forget. Okay. Also on the task there is another method that is quite important, and let's continue with. And the thing is that you can add some code that will be executed in case the tasks ends. So you can chain the tasks together, and that's in most cases way how you can for example have one task that will read some data, for example, from some stream, and then another task that will process the data, then another task that will, for example, save this to the database. But we will get to it. We will get to it soon. Okay. Any questions related to tasks or anything?
Yeah.
Okay.
Can I imagine task as the underlying layer of under threads?
In most cases, tasks, like here, will allocate some thread to process the code. But it does not need to be always the true. As I said, for example, you can have a task that waits for the network to do something, and for that you don't need tasks, so internally it will not use some blocking task to wait for it.
Will the task always try to allocate as many threads as it can to max out the CPU performance?
Yeah.
Yes.
But the task, if you get task, there is some manager, not manager, factory, and the factory got some scheduler and some properties that can help you to manage this. And also you can have task that's created from some specific scheduler that's set up specifically for some of your task. For example, the scheduler is in the beginning little bit conservative. It expects that your threads will consume a lot of the CPU. So if you start a lot of tasks, there will be probably just a small tasks running, and later more tasks will be executed at the same time. So, for example, if you are, if you know there can be a lot of tasks running at the same time, you can change the configuration of scheduler to have some better results from the beginning. But that's just the fine tuning of the application.
Okay, so there is this scheduler that takes care about allocating threads to all tasks that run at the same time.
Yeah.
Okay.
Okay, so we are getting to something a little more interesting. Is there anyone who can tell me the difference between synchronous and asynchronous programming?
Yeah.
Code goes parallel. And this is
No. That's common misunderstanding, because
it's past the
you
past the execution to different, for example, thread or something, and create the
Yeah.
state machine to wait for the.
Yeah. Because you can have asynchronous programming with just one thread.
Yes.
The thing is that you can have parallel programming when you are handling different threads running at the same time. But synchronous, it's like waiting until underlying operation will finish. Asynchronous is that, for example, I can go to anyone. I can go to you and tell you, please bring me, I don't know, coffee, and I can stand here and wait until you bring the coffee. Then I can take it and continue. That's basically the synchronous programming. If I would like to do it asynchronous, I will just tell you, please bring the coffee, and when you bring the coffee, then do something. For example, bring it to the table, or tell someone to drink it, or something else. So that's basic, and that's something I don't need threading. For example, I can just wait for the weather can be better, and I don't need anyone to just do something with the weather. I can just wait for it. So I don't need multiple threads for asynchronous programming. But in most cases, it's like having multiple threads. Okay, we will get to the details, and I will just show you some simple demo of basic synchronous programming. So, 5. I've got here some nice class called pizza, and I've got method cook. Because we are not taking care about if it's parallel programming or not, we are talking about asynchronous programming. I will not take care about what happens inside the cook method. If there is some another thread, if there is some signal to the operation system, or if there is some hidden oven and some pizza starts to cook. It's just creating some time. For example, I think it's 4 seconds, and if we call the cook, it will just block current thread for 5 seconds, and then it will just write the result. Okay, it's doing something, and it finished. Okay, this is typical synchronous programming. If you do this in some, for example, desktop application, desktop applications are mostly, in most cases, specific that it got one user interface thread, and if you block this thread for some longer time, the application will just stop responding. It's quite something everybody knows, that just application stops reacting on some user input. So if we do it something like this, then the pizza cooking will block the main thread, and just the application will start to be unresponsive. This does not need to be a problem, and we can solve it in some different ways. One way is that we can just create another thread, another task, another work item that will prepare the cooking, and then we can synchronize the result back to the main UI thread. That's one way. Another way, or another approach, is, for example, in HTTP applications. In HTTP applications, you've got thread allocated for your request, and then, for example, 90% of the time you are waiting for some blocking method to be completed. That's also you can create another thread, but it will not help you a lot, because the problem is that you are blocking thread and you don't need to block thread at the time you are just waiting for something. So, for example, in this diagram, if you don't need the thread for this time, then the same thread can be used to process also the second request, because you would don't need to just wait for everything. So there are different aspects, and the asynchronous programming try to solve all of these aspects with some abstraction. So, why cooking pizza took so long? There can be two options. One is that the operation is CPU bound. That means there are some hard-code complex algorithm that tries to calculate something, and basically we really need the thread. We need the thread to complete the operation. We can do something like parallelization, and you can split the load into multiple cores, into multiple tasks that's running at the same time. That can help you in the case that operation is really CPU bound. But there can be also I/O bound, which is basically the opposite of the CPU bound, and it means it waits for something. It waits for something that CPU will not help you with. It can be waiting for the network socket. It can be waiting for some file handle to be opened to start reading from the disk and things like that. And that's something that asynchronous programming can quite help you, because you can release the thread for someone else until the I/O operation is finished, and then you can continue. So there are currently 3 patterns that Microsoft provides for working with asynchronous programming, and 2 of these patterns are basically obsolete. The third pattern is related to tasks, and that's one that's preferred right now, and we will discuss it. We will discuss it later. So the first one is I don't know how many people here remember these begin read, begin request methods in .NET, but it's one of the way how you can tell, okay, I need you to do something, but I will not wait until it's done. Just do something until it's done, when it's done. And it was done by these async callback delegates, where you just call begin read, and as an async callback, you put some delegate to method that will be called when the read will finish. So you can do something else in the meantime. That was quite straightforward, but it gets quite complicated if you need to do a lot of these asynchronous read, because you've got lots of delegates, lots of callbacks, lots of synchronization, and it gets pretty messy. It was okay for something, but if you are using it for a lot of operations, then not very pleasant to work with. Okay, another one, which is something that is not used a lot. The first one is widely known, but the second one is having some events. So you call work async something, and also subscribe to some event that will be invoked in the case that operation is finished. It's very similar to the first one, but you just use the events instead of parameter to the begin read method. And third, currently preferred, is task-based asynchronous pattern, which is using methods that returns tasks and ends with a keyword async. That's something you can see in the latest version of .NET Framework, where you've got a lot of methods, for example, open, and then you've got open async, read async, and basically the variant without the async is synchronous blocking operation that just frees your code until the process is finished, and there is this async that will return you result immediately, and they will return you the task, and the task will manage the state of the processing of the current operation. So typical use is that you call work async, then you can do anything you want, and somehow you hook to the task complete event, and then do something related to processing the result from the task. Also, this is quietly integrated with the async await pattern, because async await pattern, it's exactly the automatization that helps you to write more easily these async methods and use tasks inside your methods. Okay. Prefer way how to write application. Okay. Always return the task. It has async suffix and more pizzas. Demo. Sorry, no real pizzas. So. So this is, I also got two options here. First is fully synchronous. We've got two pizza objects, and then I will cook both pizzas. It's synchronous, so I'm doing it one after another, which is quite. It doesn't make sense. If you've got oven, sorry.
If you have only one oven, it makes
You
sense.
can have large oven.
And two large pizzas.
This is pizzas that gets delivered also with oven, so it's okay. And that's the thing, you don't need to care about what's happening inside if you are using these async things. You don't care about if it's another thread or if it's calling some cloud. Okay, so if I do it like this, and one cooking takes 5 seconds, it will take 10 seconds to process, which is pretty standard stuff. But how to use it if you are using this task-based asynchronous programming? You can start cooking both. So you start cooking first one, store the task to some variable, and immediately you get to another command. You also start cooking second one, and then you can use task wait all, or you can use pizza one task wait and pizza two task wait. It doesn't matter. Just this wait all will wait for all given tasks at the same time, and then you wait for the both pizzas to be completed. So it should be much more faster. Okay, cooking two pizzas. Okay, 10 seconds, and if we are using these tasks, it's in the 5 seconds, because that's something that can be quite a good run in parallel. Okay. It helped us in this case because we got two tasks that we want to run at the same time. That's pretty helpful, but still there is one problem, and that's this wait all method, because this wait all method will still block our main thread, and we are not doing anything. It just keeps here and waiting for two tasks to be finished.
We can use when all or something like this.
Sorry?
We can use when all instead of wait all.
It's exactly. Yeah. I know what you mean. Yeah, it's possible. I will get to it. Okay, so if you are doing something like this, that's exactly what I have here on this diagram, and you are using the thread all the time. Of course, you don't need to care about it a lot if you are doing something really simple. You need to care about it in case you are working with some desktop application when you don't want the thread to be blocked. And also you care about it in a server application when you want to be able to process a lot of parallel requests at the same time without just allocating the full thread for all the time. So, we want to do something like this. We want to have our thread only to prepare the task, and then just return to the task to someone. It depends on your threading model, on how the application, what kind of application you are writing. Then just return the thread to someone, and then just continue when the task will finish. And there is something in the .NET that can help us with this, and it can help us even if we are using web application, desktop application, and that's the synchronization context. Have you ever heard about synchronization context in .NET framework?
Yes.
Someone probably is. And so, what's the synchronization context for? And it's magic. That's a good thing, because it just works automatically. If you are creating the web application, then automatically the synchronization context is set to web application synchronization context. If you are using WPF, synchronization context is set to WPF synchronization context. And if you are using async await, it uses the synchronization context. So it's basically, if you ever used the async await, you used synchronization context, and you probably don't even know about it. So what does it do? It provides the implementation of different synchronization model. Okay, that doesn't help a lot. So it defines how application will run the code until the asynchronous operation ends, and that's exactly the problem we need to solve. Because if we start, for example, on WPF application, some asynchronous method, we can return to processing for regular, for example, input events, and then we need to do something when the operation ends. So what are the types of the synchronization context in .NET Framework? There are basically three. First one is no synchronization. That's default for console application and things like that. Because if you tell the task that it should do something after some asynchronous operation ends, it will just use the thread from thread pool and just execute your code in some new thread, which can be okay for console application. But it's not very okay, for example, for WPF, when you want to return this call to the user interface thread, because if you want to manipulate, for example, with your UI components, you cannot do it from other than UI thread. So I will just show you a simple demo that can give you an insight how it works. And also there is some ASP.NET synchronization context that, for example, takes care about settings current context on HTTP context to your thread that will be spawned to finish the request, and it does a lot of other stuff. Okay, so yeah, and async await. That's the reason why that's the way we can use this synchronization context without knowing there's any synchronization context. Okay, so let's see one of the demos. Okay, so I've got simple WPF application, and there is one component. I don't know if you are familiar with the WPF, but basically we've got one component with a label, so we can change its text, and we've got one button, and that's basically it. And I've got pretty standard code here. I will just call cook pizza and then write to the label pizza is ready. Let's start it. And I'm also logging the number ID of the thread that is executing the code. In this case, it will be definitely the UI thread, because the UI thread also invokes all the events on the buttons and everything. So there should be identification of thread. Okay. Okay, I'm waiting. Application is currently don't do anything. Okay, and the pizza is ready. The application just froze for a moment, and I can see here that there is thread 1, so it used the first thread. If I execute it again, there should be also the thread 1, because it's still the same UI thread. Okay, it works, but it's synchronous and it blocks our UI. And basically, unblocking UI is one of the main reasons why the asynchronous programming is get to the is inside the .NET framework integrated, and in the C# with async await keywords. But it's not the only reason. Another reason are these server application when we need to not waste with the threads. But at least using the async await, we can both in the desktop WPF application and in the web application we can use exactly the same patterns to achieve what we want. Okay, it's a little bit after 3 p.m. So we will have 10 minutes break, and after the break we will continue and we will rewrite this to the asynchronous code, and then we will use it in the web application. So in 3:15 we will continue. Okay, so I will continue with this code. This code, I'll just close the door and so people cannot get in. With this code that tries to do some blocking synchronous operation, and how to rewrite it using the task asynchronous pattern. So first thing we can do is of course to create a task. Run it in a task, but because this pizza class supports async, so it got this async version of the method. So we don't need to create task that will wait for it, because it will be wasted one thread that will be on the blocking operation. So we'll just try to start the task. Also, one important thing: these async operations. Chocolate arrived. Time for a question. Pay attention, there will be questions. If you call this async method, it should return the tasks that already started. So you don't need to start the task that this async method returns. And how to work with it? We can of course call wait, but it will not help us. We will just block the current thread to wait for the result. What we can do is to use the continue with. And here we can just place the code here, and if we do it like this, then the method will start processing. It will create task, and it will tell that after task ends, this task will be invoked. This will work because it will work partially, because it will end event handler immediately. So we can the UI thread will not be blocked anymore, and we can still using the application. But there will be one problem. Anybody knows what will be the issue with this solution?
Is it marshaled back to the UI thread? Like this?
Yeah, exactly. That's the issue. It will not be marshaled back. So if we call it, I'm not sure if I click. No. Okay, you can see it's in the thread 1. It will do some processing, and then it will throw in an exception that the calling thread is not. The calling thread is different, that owns the label 1 component, which means that it's different thread that is the UI thread. You can see it like here. There is thread 1 and thread 7. So there is some different thread that is processing the continue with, because it makes sense, because the UR thread is it's fully used by the WPF for rendering, for processing. So there is no some common way. So thanks. There is no some way how we can tell how to get it back to the UI thread. And that's exactly the reason why we are having the synchronization context. The synchronization context for the WPF will take the task and schedule it to the UI thread, because WPF have something called dispatcher, which is basically the queue of the events that needs to be done. There are queued all events, rendering, and things like that. And this this synchronization context will help us to get the code there. So, how to do it? We can do it manually. It should be synchronization context. Task scheduler from current synchronization context, and we will just use different task scheduler, because default task scheduler will just use the thread pool to just allocate some new thread in which the task will be processed. If we used this, then the task will be returned to the original UI thread. We can try to run it, and it should work. Okay. Okay, pizza is ready. It works. But this is the way how you can work with it manually. Basically, right now we did what the async await can do for us without doing this magic about continuous synchronization context and things like that. So let's rewrite it to the async method. Internally, the code is translated and it will use something like this, and it will do exactly the same thing like we write here, but we can use the async method. So how to do it in the WPF? Of course, it's can be done differently in ASP.NET MVC. It can be done differently in ASP.NET Web Forms, and it can be done differently in WPF. In WPF, we can just mark this method async, and here, instead of creating task and defining what will happen after it, then we can use the keyword await. So I will just put here await, and then I can just remove all of these stuff. And maybe I can comment the original one. Okay, perfect. So, the first question related to the chocolate. Can you tell me what will happen here when I run the code? How the method will be processed?
Yes, I can. At the await comment, the processing of the calling will be returned to the caller, and after the cook async will be finished, the method will continue.
Okay, yeah, it's exactly like that. So when the event will start, then these lines will be called immediately, and then the method will end. After that, when this task will be finished, then synchronization context will be used, and the second part of the method will be invoked on the UI thread. And that's basically what the async await does, and what the synchronization context does. So this will help us quite a lot to use these awaits without creating tons of continuous. And internally, it will break the method to some state machine that will be split it into parts split it with the await keyword. So there will be first part that will run immediately, and the second part that will run after the awaitable will finish, and it will be returned to the main thread. Okay. So we can just try it if it works. okay, it works, like, because, yeah. I saw that if I move over, the button is glowing, so it works. So in this case, we didn't need to use any kind of synchronization context. Okay.
I was going to ask a question. Why there were 6 threads written in the console? Why 6?
That's the identification. It's not deterministic. So it's just there are a lot of threads inside the .NET application domain that takes care about different stuff like garbage collecting and things like that. So it's just coincidence. It does not need to be thread 1. Okay, so we've got it right here, and I would like to point out one very important thing. We are creating async void. This is something you should not do in your code. It's specific for the events. In most cases, you would like to just return just like this. Because if you do, if there is no return value, then this method will not return the task. So the caller will not be able to find out if the task has been finished or not. This is something very specific for WPF, where the void needs to be used. But if, for example, in ASP.NET, both web forms and MVC, you should always define the return value, at least like a task without generic parameter. Okay, so any questions related to the synchronization context? Okay, so I will move to another chapter, and that's how it's implemented in ASP.NET MVC. That's quite helpful because ASP.NET MVC get also implemented the asynchronous controllers, and you don't need to do anything too complex to start using it. Okay. So I've got here some simple web application with one controller or multiple controllers, and this is the first example. As you can see, if I do it like this, I will use the async method, but still there will be the blocking with the wait. So this will not help us because all the time the pizza is cooking, the thread needs to be allocated for this HTTP request. It will work, but it will not help us a lot. Another way how to do it is exactly with this continue with syntax. So you can return the task from the controller, if from the action. If you do it, it's automatically the asynchronous controller, so it's supported. But in case you will do it like this, I'm not using async await helpers that can help me to write it easily. I'm just trying to build the tasks from the code and not working with the async await keywords. If you are writing async method, it for a caller, it doesn't matter if you used async await keywords or not. If you are building your async code by these commands, it doesn't matter. But also you can use the variant with the async await, and it can look like this. So you mark it as an async. If you mark it as an async, it means that it will split the method to the parts, and you can use the await keyword, and it will just get here, start processing the task, and the thread will be returned to the thread pool, and it can be used to process another request. And after that, when this will finish, the thread, maybe another thread will be taken from the thread pool, and it will finish the last part of the method, build the result, and return it to the client. Maybe you can, there are some thread-specific data, like for example UI culture, current user, and things like that. And that's something that the async await does for you, and it's pretty complex how it works inside, but you can just use it and don't need to care about it, because it can happen, and it will probably happen that this and this part will happen on another threads. This will not be the same thread, but the synchronization context will take care about moving context from this thread to this thread. So you here you should have same culture, current logged in user, and everything like here in this first thread. So you don't need to care about it that it's a different thread. It's something that works really automatically. But if you wrote some asynchronous programming in older versions, this was quite a problem, because you need somehow to pass, for example, logged in user details from one thread to another. And we can test it quite easily. I can start the performance monitor. And I will add some counter for .NET. We need .NET looks and threads, number of logical threads, and we will check number of logical threads for IIS Express. Because we are using the IIS Express, there is quite limited number of connections that can be processed at the same time. So it will not be somehow dramatic, but we should be able to see it. So we can see there are just few threads there, and I will create from here some kind of request. Should be pizza 3, and pizza 3 is using the async await. Okay, pizza has been cooked. It took some time, but it works. I will create a request, and I will create huge amount of few requests. And you can see that the number of threads is not increased a lot. Maybe there is few more threads allocated, but it still can work. It still can work with quite minimum load. This is extremely useful. For example, if you are doing some kind of routers that does not need to do some heavy CPU processing, that just waits for the resources. For example, from some SQL server or from the network, from some other service. But if I use the first version with the blocking, let's see if it do something. You can see it increases the number of threads because it needs as many threads as the requests are processing at the same time. It's still not much, but of course, if you try to do some measurement related to thousands of requests, yeah, then it will completely goes up, because there is nothing that application can handle these numbers of requests, because it's basically does nothing. It just allocates threads. So you should be able to see thousands, for example, 1,000 thread, and or there are some limitations, but it's really a big difference. And it's basically you can use it for free. You don't need to do some extra implementation, and in most cases the libraries are ready to use these async methods. Okay. Yeah. So this is basically how you can use it from the ASP.NET.
We can or we should?
You should. It's something that .NET is trying to go in everything, and they are already removed some, or on the new libraries they don't implement the blocking operations.
I'm asking because I'm new to ASP.NET. I was working as a developer, WPF developer before. So the scaffolding system has only the options for to use the async operations in controllers. So I am wondering why this is not the preferred one option and something like this.
Well, it's more like there is some progress, some steps they are taking care about but basically everything they are releasing now is they are trying to make it async only, and
Okay.
it's just all templates. These templates quite a suck. So
Okay.
okay, so this is some usual method you can use where you can use the async. So for example, this is some HTTP client that will read something from some address. You can see that there are two awaits here. So if you are trying to write it with a continuous, it will be two nested continuous. That's quite mess. And also these using statements are quite hard to implement if you are writing it with a continuous, because this async await will take care about disposing after, for example, if for example this fails, then it will automatically dispose the response. So it will act like you are writing the regular C# code, even if it's split it into different parts and it's executed on different threads. So you can use it like this, and for example, it can help you quite a lot. Once I wrote one application that does exactly something like this. It just downloaded source from another endpoint and just pass it to the client, and it was quite a large files, and there was quite a heavy load on the server, and just switching to the async quite a help with the performance, because there was no more waits for basically empty thread pool. There was some queue for the request, and this queue was full because it was waiting for the threads that was just sitting there and waiting for the data from third party service. Okay, so related to this async, just don't remember that if the method is async or not, it doesn't matter. Important is that you are returning task. Everything you are returning task can be, basically every task can be awaitable. So you can await any task, even if it's not the result of the async method. Async method is just a helper for you to write it more easily. Okay, so we already saw this. So I will just move to the last slide. We make it a little bit faster, and just few takeaways I would like to talk about. First thing is the asynchronous is not parallel programming. Asynchronous, as we discussed it, is just not be blocked by waiting for something, and it doesn't matter if this something is another thread or if it's waiting for some I/O operation. Parallel programming is exactly the different thing. Parallel programming helps us in case we would like to split the CPU load to different threads. It happens a lot that if there was not good support for asynchronous programming in .NET, then if someone needs some thread to not be blocked, they just created, for example, task or some thread, and this thread was doing only that it was waiting for some blocking operation to finish, which is the waste of the resources. So currently there is no reason to not use the asynchronous if it's supported by the application you are writing. Also, you don't need to implement async await everything. It's quite a good pattern to support async everywhere where you are using some async API. So if you are, for example, using some third-party library that's got the async methods, then write also your method that is using this library as async. And in most cases, you will get all the way up, for example, to the async controllers. It can happen in some cases that your controller, for example, or the code that starts your some of your method is not asynchronous, but your class, your API is. In that case, you can use these waits to just do the blocking wait for end of the operation. Of course, it's not ideal because the thread is blocked, but still, if you are, for example, using something that does not support this async, then you've got no option. But it does not. But it should not block you from making your API async as well. Another thing I already mentioned it is if you're creating the task, always try to read the result of the task. Don't use it like a fire and forget. Just create task, start it, and forget about it. You should always read the result, because that's exactly what await does. Wait for the result, and if the task fail, then this line will throw you an exception. So it will act just like there is some direct exception thrown at this line. So this awaiting or calling await or task wait all or something like that, it will read the result of the task, and it will pass only in the case that the task worked. In the other cases, it will throw an exception. But don't just create task and forget about it. And as I already said, try to not use thread pools. Try use the task whenever, if it's possible, whenever it makes sense. Okay, so that's basically everything from me. If you've got any question, just come here, or if you want the chocolate, it's here for you. So have a chocolate and have a great weekend.
Technically, one case, if I forget, when I'm using UDP datagrams,
Yeah.
I'm firing and forgetting.
Yes, but you should still probably handle the exception.
In this case, nobody cares about it. You know, it happens or not. That's the principle.
Yeah, I would maybe ignore exception in that case, but there are, for example, logging frameworks that will hook on the unhandled task exception. So maybe just ignore it, maybe just prepare it for some logging that something didn't go well. I don't know. In this case, it can be just empty try catch, but the processing of exception can be a little bit expensive. And as I said, there are configuration when it is set to true, it will crash the application in case you will not handle it. And because it can happen that in some cases there will be some issue related to tasks, and if you try to debug it, then you want to catch exactly these types of the unhandled exception in the tasks, and in that case I would prefer just try catch to the empty. But it really depends. But this is really some cross-cutting concerns. That's not.
Yeah, that's when I'm looking to UDP, so right.
Yeah.
I have no option but.
Yeah. But you, for example, would like to know that, for example, this UDP client somehow broke, that is invalid state.
Basically the message connect the cable is good to fix it.
Yeah, but it's
basically
really
the principle
core.
is, but this one is.
Yeah, there is always exception to the rule. So.
And is this some reason when not to use async await, because it tells every controller or every method in the controller should be. But if it's really atomic method,
I don't think it makes sense right now to just do async method, because you can if you don't call any async inside. But I don't see any issue. The only issue can be, for example, if the framework you are using is not supporting it, because ASP.NET MVC is supporting it, because you can create async, you can return the task, and of course there can be some problems related to the synchronization of threads or anything else. But this can be also some quite corner cases, and just to remove it in case there is really wrong something with it. But it's
basically if the method in controller contains some return view.
Yeah. In that case, you don't need to do it because it doesn't make sense. If you are not using the async in it, you don't need to have async method.
And you mentioned the context with thread cultures. Do you think that in ASP.NET is better to store it there or store it in each request context?
It's in the bold. It's both in the thread.
Yes, we faced this problem with Intelligent because they were losing the context in the inside the threads.
I heard that this thread context transferring was the hardest thing about async await, because it's quite a complex. Maybe it looks simple, just copy some values, but it's really hard, and it should work quite well. And maybe that's the reason why they are trying to remove this thread-specific and static things from the .NET Core.
Yeah, in the .NET Core it's removed.
Yeah,
it's
and that's
to reach the request context.
Yeah, and that's exactly the reason why they did it. Because they just don't want to rely on some static stuff.
How to, for example, realize a counter in task? For example, if I want to show a message, your pizza is ready 25, 26, 27%.
Sure. There are two ways how to do it. First thing is that you can have task that will just.
Is there some state or something ready state?
You can have there some task event. That's one way. Or you can just have some methods that will not await the whole operation, but they will just await until the state change. And state can change, for example, just a person. So you can have the while loop
so
there.
So tasks have their own state, yes?
You can have there some while loop, but it will in most cases it will just thread will be released and it will just wait for the state to change.
Okay.
So that's something also you cannot do without the async and releasing the threads. So. Okay, perfect. So have a great weekend. Have a chocolate.